Hello everyone, welcome back. Today I'm going to explain a problem on deflection. A concrete beam having a rectangular section 150 by 300 mm is pre-stressed by a parabolic cable at an eccentricity of 75 mm at midspan towards bottom or soffit and at an eccentricity of 25 mm towards top at support section. The effective pre-stressing force is 350 kN. The beam supports a concentrated load of 20 kN at center of span in addition to the self weight with a span of 8 meter. Find the short-term deflection at center of span under pre-stress, self-weight and live load. Also, find the long-term deflection if the loss ratio is 0.8 and the creep coefficient is 1.6. EC or Young's modulus of concrete is 38 kN per mm square. So let me explain what they have given. First of all, the rectangular section dimension is cross section of rectangle is 150 by 300 mm. That is width is 150 mm, depth is 300 mm. So obviously neutral axis will be half of the depth. It will be at a distance of 150 mm. And the cable is parabolic in nature. It is having an eccentricity of 75 mm at midspan. That parabolic profile or cable is having an eccentricity at the midspan exactly at the center, that is 75 mm towards bottom and at an eccentricity of 25 mm towards top at support section. These two words are important, top and the bottom. Why? Because 75 is present below the neutral axis. This 25 eccentricity is present above the neutral axis and it is present at the support section. The pre-stressing force value is 350 kN. Beam supports a concentrated load, that is a point load of 20 kN at center. Along with that, self weight is also there. Self weight is nothing but it's a dead load which is acting throughout the beam. Length of the beam is 8 meter. We should find out how much is a short term deflection at center of the span and how much is a long term deflection. These are the given datas. So I have written all the given datas. P equal to 350 kN, loss ratio is 0.8, phi is 1.6, EC 38 into 10 power 3 Newton per mm square. So just now whatever I have explained, I have just drawn and I have shown. See here, it's a parabolic variation. So this neutral axis, this is dotted line as a neutral axis. Above this is 25 mm at the support. Below this it's 75 mm at center. These two are pre-stressing force, and you can observe this cable or this parabolic cable is not ending here on the neutral axis. It has got extended and it is ending or it is joining where we have 25 mm. So like this you should draw the parabolic cable profile. Self weight is acting, so it is nothing but it's a dead load. It is in the form of UDL, point load 20 kilonewton. So let's start with the calculation. So to find out a deflection due to short term, deflection due to long term, how we should start is, first of all, we know short term deflection occurs due to dead load, live load as well as a pre-stressing force. But this long term deflection occurs due to dead load, live load, pre-stress and creep. So along with these three things, that is dead load, live load, pre-stress, creep is a additional thing in a long term deflection. So we should start calculating deflection due to dead load. To find out how much is a deflection due to dead load, first of all we need to know how much is the dead load of a beam. So I have calculated dead load of the beam, and we require I, that is nothing but moment of inertia, to find out the deflection due to dead load. Here you can see I term, so I is also important. Moment of inertia I equal to BD cube by 12 equal to width is 150, depth is 300 cube by 12, it is 337.5 into 10 power 6 mm power 4. Dead load of the beam, we know how to calculate cross section into density. Cross section I have converted from mm to meter, so it is 0.15 into 0.3 into density is 24 kilonewton per meter cube, so take 24. We will get 1.08 kilonewton per meter. First calculation is deflection due to dead load. For that, delta dl equal to 5 by 384 into WL power 4 by EC into IX. How did I take this formula is, it is a formula for a dead load, that is simply supported beam carrying a UDL. When we have simply supported beam carrying a UDL in dead load, that is UDL is dead load, we should consider this formula, and notation for the deflection is delta dl. So substitute the value 5 into W, that is nothing but dead load of the beam, we know it is 1.08, just convert that into Newton per mm, it will be 1.08 only, into then length is 8 meter, I have converted it into mm, so 8000 power 4 by 384 into Young's modulus of concrete value and I value. Substituted, we will get 4.49 mm has a deflection due to dead load. Deflection due to dead load is over. Next slide is about deflection due to live load. Deflection due to dead load is over. Second part is deflection due to live load. For that, how did I take this formula is, you can see the notation, it is delta LL deflection due to live load equal to WL cube by 48 EC into IX, where this WL cube by 48 EC into I, how did I take this is, here in problem live load is point load. So for point load, formula is this one, that is simply supported beam carrying a point load exactly at this center, formula should be this one, take it, be careful while substituting W, here W should be 20, that is point load, 20 into 10 power 3, there it was 20 kilonewton, I have converted it into Newton, so it is 20 into 10 power 3 into 8000 cube by 48 into EC and I value. We will get deflection due to live load has 16.63 mm. The third one is deflection due to pre-stress. This is important point, that is how did we write this two variations here, or why did we write this two variations? In previous slide, you can observe from here to here it's a parabolic variation, and from here to here it is almost like a straight cable. So because of these two reasons, we have drawn two bending moment diagram there. I will let you know why did I write this, or how did I write this rectangle one. Always for a straight cable, the bending moment variation is rectangular. So you should take rectangular bending moment diagram, and it is having a eccentricity of E1. Here you can observe this 25 mm is E1. So from here to here it is 25 mm. Consider only this rectangle portion is between these two lines. So obviously P into E1 is a height, and the width is, it is half of the length. The complete length of the beam is 8 meter, half of it is 4 meter. Convert it into mm. So 4000 mm. Consider only a half of the portion, which I have shown it by hatching it. Straight cable portion is over. The next thing is for the parabolic profile. For this parabolic profile, it is obvious that the bending moment diagram will be a parabolic, but you should observe one thing here is, here when we write a parabolic variation, at the top it will be P into E1 plus E2. Don't forget to add both the eccentricity. We should add both the eccentricity. So P into E1 plus E2 is a value. Again, the length is L by 2, that is nothing but 4000 mm. But one more important thing here is the sign. If the profile is below the neutral axis, this line is a neutral axis. So this parabolic profile is below the neutral axis. So it is obviously, it's a negative bending moment. Either you can write a statement here, or you can directly show a sign here that it has minus. Like that, for a rectangle section, here I have written it as positive bending moment. How did I write that? If any cable is present above the neutral axis, that portion is obviously a positive bending moment. Here the straight cable is present above the neutral axis, so it is positive bending moment. If the cable is present below the neutral axis, it is present in the form of parabolic, so parabolic variation is there, but sign will be negative bending moment. We need to calculate deflection due to pre-stress. So for that we require this P E1 and P into E1 plus E2. So I have calculated those things separately. Then I will consider these values directly in the formula. Like that, for the first one, that is for a rectangular variation, rectangular bending moment, P into E1 is 350 into 10 power 3 into 25, that will be 8.75 into 10 power 6 Newton mm. For a parabolic, it is P into E1 plus E2, that is convert kilonewton into Newton. 350 into 10 power 3 into 25 plus 75 will give you 35 into 10 power 6 Newton mm. In next slide, it is a calculation of deflection due to pre-stress. So the standard formula for the calculation of deflection is area into centroidal distance by EI, where X stands for centroidal distance. So we are going to implement any formulas according to this. Deflection equal to area into X by EI, where delta equal to PE L square by 8 EI minus 5 PE L square by 48 EI. That is, this formula is for a straight cable. PE L square by 8 EI. This formula, that is 5 PE L square by 48 EI, is for a parabolic variation. And the most important thing is about this sign. Go and check the previous slide. For the previous slide, I said the formula is PE L square by 8, but here we should refer the sign. The sign is positive bending moment. Okay, as it is the cable are present above the neutral axis, it is positive. So I have considered plus into this formula. For the second one, that is for a parabolic, the sign is negative. So because of that, I have considered this negative sign. These signs play a very important role while calculating deflection of pre-stress. Please be careful while substituting it. So what I have done, I have just taken E into I has a common. I have written outside and I have written like this. You can write the formula like this, or you can split and write also. Okay, after calculating or after simplifying, we will directly directly get the formula like this. But if you want to split and write, that is in this form, area into centroidal distance by EI. If you want to write like that, then you can write like this also. So I have mentioned it as or. Delta PS equal to 1 by EC into IX is a common thing. So I have written outside into P E1 L by 2. What is this is? This is area of a rectangle. We know the area of rectangle is B into D. Here B is L by 2. This length is nothing but the complete length is L. Half of it will be L by 2. So L by 2 into PE1. I have written the area of the rectangle into centroidal distance. Always centroidal distance should be measured from the support towards the center. So from the support towards the center, it will be obviously L by 4. As base itself is L by 2, again half of that will be L by 4. Like that I have written L by 4 minus area of the parabola. Area of the parabola is 2 by 3 into length of this portion is L by 2 into height is P into E1 plus E2. See here, I have written the area of the parabola into centroidal distance is 5 by 8 into L by 2. From where it is measured? It is measured from the support. So from the support to the center, the centroidal distance is 5 by 8 into L by 2. I have written in a general manner. So now I'm going to substitute the values for these things. Delta PS equal to 1 by, substitute the value for EC, that is Young's modulus of concrete, into moment of inertia substituted into P into EI. Directly we have a formula. Already it has been calculated. How much is that? It is 8.75 into 10 power 6 is a value. I have substituted into L by 2 is 4000 into centroidal distance is half of this. So it is 2000 minus area of the parabola 2 by 3 into L by 2 is nothing but 4000 into this part is calculated. P into E1 plus E2 is 35 into 10 power 6 Newton mm. even, that is substituted into 5 by 8 into 4000. L by 2 is 4000. After simplification, we will get deflection due to pre-stress is minus 12.74 mm. Don't forget to write the signs. Signs are very important in deflection calculation. So it is minus 12.74 mm. Next thing is about the calculation. In the question, they have asked us to find out short-term deflection. For that, the formula is delta equal to delta DL plus delta LL plus delta PS. Deflection due to dead load, deflection due to live load, deflection due to pre-stress. Substitute all the values here along with their signs. So delta will be 8.38 mm. Long-term deflection. Now for the calculation of long-term deflection, formula this long-term deflection occurs due to dead load, live load, pre-stress plus creep. For that we have a formula as delta equal to delta IL plus delta IP into PF by PI into 1 plus 5. This formula is available in the code book. You can go and check directly, you will get there. But you should focus on the first term, that is delta IL. As soon as you see delta IL, don't jump into the conclusion that it is deflection due to live load. No, don't do that. It is nothing but it is the deflection due to both the load, that is dead load as well as a live load. So those two values I have substituted. Deflection due to dead load, deflection due to live load is equal to delta IL plus how much we got for deflection due to pre-stress. It is in terms of negative. So minus 12.74 into loss ratio is PF by PI. They have given in the question itself. So it is 0.8. And one more important thing here is, if they have not given a creep value, that is phi value is not given, means directly you can assume and write it as 1.6. But here in the question they have given, substitute that, we will get deflection or long-term deflection as 28.41 mm is a deflection due to long-term. Next thing is, but permissible deflection. How did I take this permissible deflection is, these deflection signs will play important role. Okay. As soon as I saw this delta equal to 28.41, and the most important thing is sign. If it is positive, then obviously deflection will be downwards. If we get negative sign, then deflection is upwards. So based on that, I have considered this formula. I saw here it is plus 28.41. So I took downward deflection equal to span by 250. If it's a upward deflection, we should consider span by 300. Okay, but it's a downward deflection, span by 250 is nothing but 8000 by 250, that is equal to 32 mm, hence it is safe. How did I write or how did I say this as safe means, you should check the value of deflection due to long term and as well as permissible deflection value. Here permissible itself was 32 mm. Up to 32 mm downward deflection value can come. But here how much we have got? We have got 28.41, which is very less than, or it is within the limit. It has not exceeded, it is within the limit, it is within 32 mm. So the structure is safe. Hence I have written a statement that hence it is safe. Like that we can calculate what to say, deflection due to short term, long term, and permissible deflections and all. Hope you have understood this problem. Thank you.